So as you could see, determining if a set is a vector space can actually be quite a bit of work. So rather than proving all the different kinds of vector spaces that we might commonly see, I'm going to just go through some common vector spaces. And for the most part, we'll do this without proof. So if you want to, you could confirm that these are in fact vector spaces on your own. Okay. So we have the original, of course, Rn with the standard arithmetic operations, vector addition, scalar multiplication as usual. Okay, that's the same vector space we've been using all of this time. It's the vector space that we base all other vector spaces on. We also saw that the set of all linear functions is a vector space. Okay, now that's one we actually proved. Now, this is a degree 1 polynomial. Turns out that if you take the set of all polynomials of a given degree, that also forms a vector space. So it doesn't have to be just degree 1. We're going to let p to the n be the set of all polynomials of degree n or less. Okay, so remember, a degree n polynomial would be something like, let me give you a specific example, like 3x to the 5th minus 4x to the 4th plus 2x squared minus 1. That's a degree 5 polynomial, right? So this would be in, for example, P5, the set of all polynomials of degree 5 or less. Okay? And actually, if we just take all the polynomials of all degrees, that is also a vector space. Okay? So all of these are kind of polynomial type vector spaces. There are other kinds, of course. M sub m comma n is the set of all matrices. Let me state the dimensions first. All m by n matrices. Okay. And by the way, I'm not specifying the operations on these, the addition or scalar multiplication. They are the usual operations that you would normally use for these kinds of elements. So if you take polynomials, if you add two polynomials together, you're combining like terms. If you're adding matrices together, you're adding up the elements in the same position, right? It's the standard operations. So the set of all n by n matrices is also going to be a vector space. C, the set of complex numbers, is a vector space. A complex number is a number with an imaginary I in it. So 3 plus 2i is a complex number. It has a real part, it has an imaginary part. When you add it to another complex number, you just combine your like terms. 3 plus 5 is 8. 2i minus 4i is negative 2i. Okay. And the last common vector space we'll talk about is the set of all continuous functions over an interval, over a closed interval. So we learned about continuity in calculus, right? Continuous function is a function that, intuitively you could draw without picking up your pencil. There are no gaps or jumps or holes. That's a continuous function. If you take all the functions that are continuous on some particular closed interval, a and b here could be any closed interval. So maybe the interval would be negative 2 to 5. So that means the domain is negative 2 to 5. The domain of the continuous function is negative 2 to 5, and it's continuous on that domain. If we look at all functions of that type, then that is also a vector space.